So, quick explanation of the solution to this homework 2 problem, angle grinder, calculation of the design factor for fatigue. So what do we have? The input torque, radius of the abrasive disc, diameter of the shaft, solid, round, yes, length L, ultimate strength and yield strength of the material, friction coefficient between the angle grinder disc and the workpiece, stress concentration factor for bending here where the bearing is, and a step on the shaft, stress concentrator due to torsion in that same area. And I also include a stress concentration factor for compressive stress. I'm calculating the section modulus, pi diameter power 3 over 32. I'm calculating the polar section modulus, pi diameter power 3 over 16, and transverse area of the shaft, pi diameter squared over 4. If we know the torque and the radius of the disc, we can calculate the tangential force. So torque divided by radius r of the disc, that gives us the tangential force. And then the normal force is related to the tangential force by the friction, tangential force, friction force. So Ft is normal force times the friction coefficient. We can calculate the normal force by dividing tangential force with the friction coefficient between the abrasive disc and the workpiece. The shaft is subject to compressive stress, steady compressive stress, steady shear stress due to the torque, and then bending caused by in two planes. One is the vertical XY plane, and this is a pure bending with moment Fn times the radius. So the bending stress here is going to be just Fn times r. And then we have bending the horizontal XZ plane, and that's due to the tangential force being applied at distance L. So bending stress here is due to Ft is going to be Ft times L. Okay, so Fn times R, bending moment in the vertical plane, and then Ft times L, bending moment in the horizontal plane. We sum these moments are 90 degrees, sum them as orthogonal vector, Pythagorean theorem, square root of moment in the xy plane square plus moment in the xz plane square rooted. So we've got the resultant moment. And with this, we can calculate the bending stress moment divided by section modulus, which is here. So for this set of values, it's, as you can see, 25.5. We're not applying the stress concentration factor yet. And this is going to be the alternating stress. Okay, so after half a turn, the shaft, the area of the shaft that it will experience maximum tensile bending stress is going to be subject to maximum compressive stress. So this is the alternating stress. The mean stress is due to the steady shear stress caused by torsion and the steady compressive stress. We're going to calculate the equivalent stress of that, and that equivalent stress is going to be the mean stress. So shear stress, torque, divided by polar section modulus, pi diameter power 3 over 16. And then axial load, Fn force, we have it, Fn force by A cross-section area. Okay, so, and here I have the stress concentration factor included. I'm making it 1. A fully specified problem should include or you should extract, given information about the step and the fillet radius, the compressive or tensile stress concentration factor. Okay, so I made this 1 just for this calculations. And what do we see? The two stresses, one is sigma x, the other one is tau xy. We calculate sigma 1, sigma 2, and sigma 3 for this particular case. Again, sigma y is 0, so sigma 1 is going to be sigma average plus the radius of the Mohr circle. Sigma average is sigma x plus sigma y is 0. That is Sigma x is sigma f. So sigma f divided by 2 plus, and then radius is sigma average minus sigma x squared. So sigma, that becomes also zero point 0.5 sigma f, and then tau is going to be squared added to the second and then square root. Okay, so I have sigma 1. Sigma 2 is 0. Sigma 3, I changed essentially from the center of the circle, subtract the radius. So I have a minus here. Before there was a plus. So got sigma 1, sigma 2, and sigma 3. Calculated von Mises stress. What is von Mises stress? Sigma 1 minus sigma 2 squared plus sigma 1 minus sigma 3 squared plus sigma 2 minus sigma 3 squared. Everything divided by 0.5 by 2, that is, or multiplied by 0.5 square rooted. And I've got the equivalent stress. So equivalent stress is the mean stress. So we have the mean alternating stresses. The what is between or what we have left is to calculate the true endurance limit Sn prime that occurs in the two equations for calculating the design factor. So we're given the ultimate strength, and we know the finish is machine finish. Ultimate strength is 900 megapascals. So I'm reading Sn is 325 megapascals, and the coefficients there, Cm, material is 1, its work steel, type of stress is bending is 1, and then reliability 1, 99% reliable, so that'll be 0.1, and then size factor, because the shaft is between 0.67, 7.62 millimeters and 50 millimeters, we use the equation D, that is 18 in our case millimeters, divided by 7.62, everything at power negative 0.11. So we have the size factor. And true endurance limit would be Sn times all these coefficients. So this is the calculated value. I can now implement this equation. So design factor is the stress concentration factor multiplying the alternating stress over Sn prime, sigma alternating over Sn prime, yes, plus sigma mean over ultimate strength, everything at power negative 1 or 1 over, and I've got the design factor as 4. For early cycle yielding, this is the equation to use. This time stress concentrators are applied to both the alternating and the mean stress, so I need to change this to 1.5. If I had some value given for the compressive stress concentration factor, would change this to the respective value greater than 1. And so yeah, where's this K in torsion coming in? Have it here, so it changed the early value for N slightly. Before was a little bit over 4. Now it's a little bit less than 4. Okay, so calculating the design factor regarding early yielding, it gives us a much larger value. So it's indicative that the load line is steep and intersects Goodman lines first. So this is the answer, 3 point. Actually, let's go back to 1 here. So it's 4.02. Again, I have F, the stress concentration factor for torsion. It's implemented early here. Okay, so yeah, the answer would be the stress concentration factor calculated with the intersection of the load line with the Goodman line, not the yield line. All right, and this was it. Thank you so much for watching.